Okay, we're now in chapter 19. We're going to be doing sections 19.1 and 19.2. So be sure to read those. We're working out distances to stars. If I gave you an assignment tonight, go find the North Star and measure the distance. And I know you can look up the distance on the internet, but in this case I want you to personally measure it. That assignment could be pretty frightening because most of you wouldn't know how to do that. So that's where we're headed. How do we know the distance to these things that are really just points of light out in the night sky? So we're measuring distances. Any appropriate distance unit could be used. We could measure the distance in inches, or feet, or miles, or in the metric system, what we measure in inches would be centimeters, what we would measure in feet would be meters, and miles would be kilometers. But it turns out that those units, even though a mile is a big unit for us, compared to space, it's pretty small. So in our solar system, we've defined a unit called the astronomical unit. And the astronomical unit is the distance from the sun to the earth, which is 93 million miles. It's a long distance. It's further than you'll jog in your lifetime. But on this scale, the distance from the sun to the earth is 1 astronomical unit. Venus is a little closer to the sun, so the distance from the sun to Venus is 0.7 astronomical units. Mercury is 0.4 astronomical units. Earth is 1 astronomical unit by definition. Mars is 1.5. That means Mars is 1.5 times further from the sun than the Earth is. If you knew the distance to the Earth from the sun to the Earth in any unit, multiply that by 1.5, and that would be the distance to Mars. By the way, you may have seen on the news, we have just landed a new rover on Mars. That's
What's it called?
Perseverance. Mm-hmm. And it's large. It's bigger than a large pickup. So it's a big machine, and we'll be able to travel longer distances than any of the other rovers. Jupiter is 5 astronomical units away from the sun, which means it's 5 times further from the sun than the Earth is. And Pluto is 39 astronomical units from the sun. And there are other things that are 40 or 50 or 60 astronomical units from the sun. So that makes a convenient unit for measuring distances in our solar system. But the distances to even the nearest star is so far that the astronomical unit would be a tiny unit, and we need a bigger one. So the bigger one we call a light year. A light year is the distance light travels in 1 year. So a light year is the name. You think it's got year in it. Year is a unit of time. But it's the distance light travels in that time. And we can actually calculate it. Distance is velocity times time. The speed of light in a vacuum is 186,000 miles every second. Miles per second. If we multiply that by 1 year, we have a problem with units. So I have to change my years into seconds. I know that 1 year is 365 1/4 days, and 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. And 186,000 times 365 times 24 times 60 times 60 is 5.87 times 10 to the 12th miles. That's the distance light travels in 1 year. If you could travel at the speed of light. If you could travel at 186,000 miles per second, you could get to the moon in 2 seconds. You could go 7.5 times around the Earth in 1 second. The Mars lander that we just landed on Mars had to be able to land itself, because it takes about 20 minutes for that signal to go from the Earth to Mars or Mars to the Earth. So when that lander sent back a signal and said, "I've landed on Mars and I'm safe," we didn't hear about it for 20 minutes. How long it took to travel the distance from the Earth to Mars. And so if we were trying to control that, we would have to know what was going to happen 20 minutes ahead of time to be able to send that signal. Or think about it, when we send people to the moon, to Mars rather, there's that at least a 20-minute lag. It could be longer. And so it would be like, you dial up their phone number, and you hit send, and 20 minutes later you hear it start ringing. No, 40 minutes later you hear it start ringing, because the signal's got to go up and come back. So somebody answers the phone and they say hello, and 20 minutes later you hear hello, you say, "Hello, how are you?" And 20 minutes later, so it's a long thing. And if we go to other exotic places, that time is even further. Okay, written out, that's 587,000,000,000,000,000 miles. And that is the distance light travels in 1 year. It's a long way. So a light year turns out to be a really, really big unit. Well, distances in space are really large. There is no star within 1 light year of us. The nearest star to us is 4.3 light years away. Proxima Centaurus is the nearest star to us, and it's part of the Alpha Centauri system, and it's 4 years. So if you could go outside tonight and look at Alpha Centauri, the signal that we get, the light that we get from that star, left that star 4.25 years ago. And we see it as it was 4.25 years ago. The light from our sun takes 8 light minutes to get to us. So we see the sun as it was 8 minutes ago to travel at that speed. Well, we live in a galaxy called the Milky Way galaxy, which has a nucleus of stars, a whole bunch of stars close together, and then spiral arms that come off of the nucleus. And we live on the back edge of one of the spiral arms, and about 26,000 light years away from the center. So if we went outside and turned on a flashlight directed toward the center of our galaxy, they wouldn't see it at the center of the galaxy for 26,000 years. Our galaxy is about 100,000 light years across. It's a really big galaxy. But if you lived over here on this edge and your favorite restaurant was over here on this edge, you could say, take your girlfriend and say goodbye to your parents, and you get in your spaceship traveling at the speed of light. It takes you 100,000 years to get to the other side. You sit down and have a wonderful meal, because this is a great restaurant. And then it takes you 100,000 years to get back. And so when you get back to Earth, all the people that you knew died 200,000 years ago. There's probably no record of them ever existing. Life on the Earth would be much different than it is today, and it would be really strange. There's another galaxy in space called the Andromeda Galaxy, It's also about 100,000 light years across. It's pretty much a twin of the Milky Way galaxy. And the Andromeda galaxy is the farthest object you can see with your eyes. So if you go outside and look at the northern sky in the Andromeda galaxy, and you're away from city lights, you've got a really dark sky on a nice clear night, you can see a fuzzy area about the size of the full moon. And that fuzzy area is the Andromeda galaxy. It is 2.5 million light years away. If you go outside tonight, look up in the sky and see it, the light that you see left the Andromeda galaxy 2.5 million years ago. We're actually seeing it as it was 2.5 million years ago. And so distances in space outside of our solar system are really, really, really huge. Don't go outside tonight and look for Alpha Centauri, the closest star to us. It's not visible from Borger. It's in the southern hemisphere. But there are other stars. I think the North Star for us is 75 light years away. So it's pretty far away. Well, how can we measure distances to these objects? We can't even get close to them. There's no tape measure that's long enough to stretch from here to another star to measure that distance. And we use a technique called triangulation. In your book it's described as triangulation. Imagine a man coming up on the edge of the Grand Canyon. And that's a really deep canyon. It's about 10 miles wide, we know today. And so this man walks up to the edge of the Grand Canyon and he wonders, well, how wide is the canyon? Okay, so if we look down on it, here's one edge of the canyon, here's the other edge of the canyon. Say there's a tree over here near the edge. So to measure the distance from this edge to this edge, you would mark out a known distance. So maybe he walks a half a mile this way and puts a little telescope thing, and then a half a mile this way, and he creates a distance of 1 mile. This is called the baseline. And he measures the angle from the baseline to the tree, and the angle here from the baseline to the tree. And these angles get closer and closer and closer to 90 degrees the farther and farther away the tree is. You can do a little geometry or trigonometry, and you can then calculate, if you know the angles and you know the baseline, you can calculate the distance to that tree. And that's how we measure distances of something like the Grand Canyon. Or how far is it across Lake Meredith? You know, you would use triangulation. We won't worry about the details of the math to do that, but that's the general idea. Well, it turns out that the Earth goes around the sun. Hope that isn't surprising to you. So here we have the sun, and the Earth goes around the sun. And let's say there's a star out here, and we want to know the distance to that star. Well, the Earth is moving, but we will see this star appear to be moving, and this is called parallax. Parallax is the apparent motion of an object. An object will appear to be moving the apparent motion of an object caused by the real motion of the observer. If something looks like it's moving, it's not really moving, it just appears to be moving because you're moving. Let me show you where you've seen parallax. You're driving down the road, and along the side of the road there are telephone poles. And it looks like telephone poles are whisking by, just zipping on by you as you drive down the road. It's not the telephone poles that's moving, it's you that's moving. But it looks like the telephone poles are moving, and that apparent motion is caused by the real motion of the car. Okay? Or you might be in your car and you look down the road and there's a bridge, and you think, well, that bridge is getting closer and closer and closer and closer and closer. I better pull off and let the bridge go by. It's the apparent motion of an object caused by the real motion of the observer. Well, if the Earth is going around the Sun, one of the big arguments that said the Earth couldn't be going around the Sun is because we can't observe parallax. So parallax says that if the Earth were, say, here, and we looked at a nearby star, we would see it over here against these background stars. And then as the Earth moved in its orbit, when it's over here, we would see it back against these background stars. So as the Earth orbits the Sun, if the Earth is actually moving, then we would see the position of that star changing. And what we would see is that star would be moving in a little circle in the sky. Now, don't think I can go outside and look up and see a little star going in circles in the sky, because it takes the Earth how long to go once around its orbit? Okay, 1 year, or 365 and a quarter days. And so this little parallax circle would take 1 year to see in the sky. The way you would measure that, and it was finally done in 1893, you would look at a field of stars, and today we would photograph this area and say in a month we'd come back and photograph the same thing. Okay? And it should look the same, but we might notice that one of the stars has moved just a little bit. And then in another month, you see this star has moved just a little bit more, and then a little bit more. And in the process of a year, we would see that star move around in a circle. This is the apparent motion of the star caused by the real motion of the Earth going around in its orbit. So here we have the Sun with the Earth orbiting around the Sun, And I'm going to choose these two positions. When the Earth is there and when the Earth is there, we're going to look at a nearby star A, and this kind of solid line that you see would be the background stars. Okay. So, when the Earth is down here at E1, we would look at star A, up in this direction, and then 6 months later we would look at star A down in this direction, and so as the Earth goes around the Sun, we would see this star moving in a circle. It kind of goes from that point to that point and then back. This is called the parallax circle. And we can measure this angle. I'll just measure it real quick. That is 10, 20, 30, 40, 44 degrees. Now, we do the same, a star that's a little bit further away, like star B, when the Earth is here, we would see it against these background stars. And 6 months later, when the Earth is up here, we would see it against these background stars. And you'll notice this parallax circle is a little bit smaller, and I can measure this angle. That is 10, 20, 34 degrees. Then for star C, and the Earth is down here at the bottom, we can measure we can see it against these background stars. And then 6 months later, when the Earth is up here, we would see this star against these background stars. It'd make this little circle in the sky. And I can measure this angle. This one is 10, 20, 24 degrees. And then last, I can look at star D, and from the Earth down here, I would see this star against these background stars, and this star against these background stars. And we have a little bitty circle right there. And this angle is 10, this is 28 degrees, should be 28, and this one should be 24. So what are you supposed to learn from this? Okay. Notice that the parallax angles, the little circles, get smaller and smaller and smaller and smaller as the star gets further and further and further and further away. So if we can look at the star, we can measure this angle, then we can directly calculate the distance to that star. The distance to the star is directly related to this parallax angle. Now, stars are so far away, the parallax angle and the symbol for a parallax angle is the letter P. You're familiar with measuring angles in degrees? If we take a degree and divide that up into 60 parts, we get 1 minute of arc. If we take a minute of arc and divide that up into 60 equal parts, we get 1 second of arc. And stars are so far away that these angles are measured in seconds of arc. So they're really, really, really small. So going back to this, how would we measure? You take a picture and then throughout the year you get this little angle across here is going to be less than 1 second of arc. No star is close enough to us to have a parallax angle that's bigger than 1 second of arc. So they're really small. And that's why you need pretty sophisticated telescopes before you can actually see this. And it was in the late 1800s before it was actually observed. But the general picture is the farther away the star is, what happens to this angle? The distance to the star is directly related to the size of that angle. And the farther away it is, the smaller that angle gets. So the distance to the star is directly related to the parallax angle. So we measure the parallax angle, and from that we calculate the distance. We're going to define a new distance unit called a parsec. A parsec is the distance whose parallax angle is exactly 1 second of arc. Just like for time, the two little marks here mean 1 second of arc. And it turns out that 1 parsec, PC for parsec, is equal to 3.26 light years. So there are no stars. The nearest star to us is 4.3 light years away. So there are no stars closer than 1 parsec. So all of the parallax angles are less than 1 second of arc. Well, given all that, how do we calculate the distance to a star? And so that mathematical formula, this one turns out to be real simple. The distance to the star is 1 divided by the parallax angle. And the distance would be measured in parsecs, and the parallax angle would be measured in seconds of arc. So suppose we looked up in the sky and we saw a little circle, making one little circle in the sky once every year. Let's say the parallax angle was 0.37 seconds of arc. Then the distance, write down the equation, because this tells you what to do. To calculate the distance, you're going to take 1 divided by the parallax angle. Write the equation, put in the numbers, 1 divided by 0.37. Then using your calculators, type in 1 divided by 0.37, and you get 2.70. And you can round this off to 2 decimal places. 2.70, and that would be parsecs. Then we can change it to light years, because 1 parsec is 3.26 light years. So we're just going to multiply this by 3.26. Now, in your calculator, you've already got this number in the calculator. This 2.702702703 is already in your calculator, so you don't have to type that in again. Just hit times 3.26, and that'll give you the distance in light years, 8.81.
And that will ultimately be the final answer?
Uh-huh. 2 answers. I want the answer in parsecs and in light years.
So you want the parsec answer and light
Mm-hmm.
years.
And I want to see the equation, substitute the numbers, and then your answers. So if you write it out just like this, okay. So if you missed one, say, Mr. Brink, what did I do wrong? Okay. Did you have the right relationship? Did you substitute the numbers correctly? If you did this step and this step correctly, but your answer is wrong, then you're not typing it into your calculator correctly. And we can fix that. Or if you're not putting in the numbers correctly. Okay. A common mistake, a student would take 0.37 divided by 1. And you have to type in the 1 first. Okay. Suppose the parallax angle is 0.0013 seconds of arc. Well, how would you figure out the distance? Well, write down the instructions. The distance is 1 divided by the parallax angle. That would be 1 divided by 0.0013. And then take your calculator and go 1 divided by 0.0013, and that gives you 769.2307. So on your paper, you can round it off to 2 decimal points. 769.23. And that would be in parsecs. Then to change that to light years, you multiply by 3.26. So times 3.26, and that would be 2,507.69, and that's in light years. So again, you don't have to retype that number. Just hit times the 3.26, and that'll give you the answer in light years. I have this assignment. This is called Distance Parallax Method. I'll post it in Brightspace in the Chapter 19 module that I'll create. And so if you're not here, you can get this assignment. For each problem, you need to write the equation, put in the answers, put in the numbers, give me your answer. You need to see the equation, the numbers, and the answer. And students say, wait a minute, I'm going to have to write that equation D equals 1 over P 85 times? Can't I just write it once at the top? No, you write it 85 times. That way you'll remember how to do this on the test. Okay? When we take a test over this stuff, this is the best test grades my students have. Doing some of the most complicated stuff. Calculating the distance to a star. It's amazing. But once you know how to do it, it's real easy. Okay? So write the...
When is this due?
Tomorrow. You'll write the equation, put in the numbers, give me your answer, times 3.26 for each and every one. Okay?
Yes, sir.
Questions?